Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to lecture 35, Organic Chemistry 1. Today we will continue on chapter 8, Structure, Synthesis and Reactions of Alkenes. Addition of carbenes to alkenes. We have covered this topic in lecture 28, but we'll go over it again quick. Diazomethane forms methylene diazomethane structure under the action of light, heat, or cover metal. It releases nitrogen and form methylene. Methylene reacts with alkene to form cyclopropane. Its reaction is stereospecific with retention of original configuration of the double bond. Cyclohexene reacts with diazomethane in presence of light to form 1R 6S bicyclo 4,1,0 heptane. We also can get carbene from alpha elimination. Thus, when chloroform is treated with an alkoxide base, such as potassium tertiary butoxide, a small amount of its conjugate base anion is formed. This anion can lose a chloride ion to give a neutral species called dichloromethylene. Dichloromethylene, the carbon is sp2, the lone pair are in an sp2 orbital with empty p orbital. As we mentioned before, this reaction is a stereospecific reaction, which means that reacting with chloromethylene with different stereoisomeric reactant substrate led to the formation of different stereoisomeric products. So reaction of dichloromethylene with Z-but2ene gives 2R 3S11-dichloro 2,3-dimethyl cyclopropane, and this is a meso structure, so it's one compound. When the dichloromethylene reacts with E-but2ene, led to the formation to the mixture of racemic mixture 2R3R 1,1-dichloro 2,3-dimethyl cyclopropane and the enantiomer 2S3S isomer. Point 3, Siemens-Smith reaction. The reaction is typically conducted using diiodomethane in combination with metallic zinc and copper, zinc-copper alloy. The iodomethyl zinc iodide reacts with an alkyl to give a cyclopropane. So cyclohexene with diiodomethane in presence of zinc copper couple leads to the formation of 1R 6S bicyclo 4,1 heptane. So what's going on? The diiodomethane with zinc to form iodomethyl zinc iodide. This species, if we look to it, zinc is more electropositive than carbon, so the zinc will be carrying the positive charge and CH2 carries the negative charge. If iodide, which is more electronegative than carbon, will take the negative charge, so it will be negative here and zinc in here. So the CH2 will act as carbene. It's not free carbene. That's why we call it carbenoid. Reaction of this coordinated methylene with the alkene double bond gives cyclopropane. Because they show carbene-like reactivity, alpha halo organometallic compounds are sometimes called carbenoids. A carbenoid is a reagent that is not a free carbene but has carbene-like reactivity. Epoxidation of alkenes. A peroxy acid epoxizes an alkene by a concerted electrophilic reaction, where several bonds are broken and several are formed at the same time. Starting with the alkene and the peroxy acid, a one-step reaction gives the epoxide and the acid directly without any intermediate. So why we say it is electrophilic? This oxygen here is electrophile, and the pi electrons will attack on this oxygen, pushing these electrons to form carbon double bond oxygen, and this double bond will attack on the hydrogen, and these two electrons will attack the carbon on the double bond, forming a transition state we see in here to give the epoxide and acid, alkene, peroxy acid, to form epoxide and acid, carboxylic acid. Again, this reaction is a stereospecific reaction, starting with the cis butene with metachloroperoxybenzoic acid in dichloromethane, leads to the formation of 2s3r 2,3-dimethyloxyrane, one compound, a meso compound, optically inactive compound. Starting with trans e-butene with metachloroperoxybenzoic acid and methylene chloride, leads to the formation of 2s3s 2,3-dimethyloxyrane and the enantiomer 2r 3r 50-50 racemic mixture. Here we can see that this is a meso because we have a plane of symmetry within the molecule, internal plane of symmetry. Acid-catalyzed opening of epoxide. Here is a epoxide treated with acid, dilute acid, protonation, proton transfer. The lone pair of the oxyrane will pick up hydrogen to form oxonium ion. Water molecule will come and attack on this carbon and open the oxyrane ring, followed by proton transfer. So water in here will act as a base and deprotonate the molecule to form diol, and as you can see, OH up, OH down, it's anti-orientation. Okay? Just clear with one more example are 2-methyloxyrane protonation first, proton transfer, then nucleophilic attack. As you can see, the nucleophile will attack on the carbon carrying more substituent to form oxonium ion. Proton transfer once again to give S-propane 1,2-diol. Remember that we have only here one chiral center. This is not chiral center. This carbon has two identical group, two hydrogen, so we have only one chiral center, RS configuration. Just to clarify the point here, why the oxygen of water will attack the more substituted. If we look for the intermediate protonated oxirane, we will find that this is in resonance with either the partially positive 1B on that carbon or on that carbon. Of course, as we know that the tertiary carbocation is more stable than the secondary carbocation, more stable than the primary carbocation. Here we have a primary carbocation, and here we have secondary carbocation, so the contribution of the secondary will be more favorable in the resonance structure, and the oxygen nucleophile from water will attack on this carbon. Stereoisomers as products predict the major products of the following reaction: Z-hextoene with metachloroperoxybenzoic acid in acetone, then dilute aqueous acid. We have the Z-hextoene. I draw it that the double bond will be on the screen and two hydrogen are behind the screen and the two alkyl groups are out of the screen. When you add metachloroperoxybenzoic acid, then the epoxide will come from up or from down, forming a mixture of two enantiomers, 2R3S, 2S3R to methyl 3-propyl oxirane. So this is a racemic mixture. Then we treat that with acidified water. In this case, the OH will come from down to this carbon or to that one. Again here, up on that one to form 2R3R hexane 2,3-diol or 2S3S, and the 2S3R will form the same. This compound is the same as this one, and that one is the same as that one. So again, we will get a mixture of two enantiomers, racemic mixture. Let us examine the previous example. Is the product chiral or achiral? Are the reactant and reagent chiral or achiral? Z-hextoene is a chiral reactant. It has a plane of symmetry. The two faces, the upper one and the bottom one, are a mirror image to one another. Okay. Now, when we get the oxidation done, we have 2R3S, 2S3R. They are each one individually chiral, but a mixture of two enantiomers will give racemic mixture 50-50 optically inactive. We can make several generalizations about reactions that form stereoisomer. Can you explain why each of these generalizations is true? If we start with a chiral starting material, that it gives enantiomeric products will yield to a racemic mixture. Racemic mixture because enantiomers are equal in energy, even the transition state, even in the intermediate. So if we start with the same starting material, a chiral, and get to the transition state which form enantiomers, okay, as enantiomeric structure would be equal in energy, and we get the product equal in energy. Typical ideal transition state energy and products. So we get a racemic mixture. A chiral starting material that reacts in a chiral environment. A chiral environment means chiral catalyst or chiral solvent may yield to different amount of each enantiomers. Okay? The transition state is very important. Why? The transition state are distereomers. Distereoisomers means that they are different compounds with different energy levels. Distereomers and can have different activation energy. So if we have different activation energy which led to the same even compound or enantiomers, the transition state is distereomeric, which means that the rate of their formation will be different. Okay? Sharpness epoxidation is an example for that. What that scientist did, he started with allyl alcohol, a chiral starting material. Two phases are enantiotopic. Then he treats them with tertiary hydroperoxide as oxidizing agent to form epoxide. But he added titanium alkoxide and optically active diethyl tartarate. When he did this mixture, he gets the epoxide in the upper enantiomeric excess. When he used the allyl alcohol with titanium alkoxide and tertiary butyl hydroperoxide, but in this case he used RR diethyl tartarate, he got the other enantiomer from the bottom. Why? Because this mixture, titanium alkoxide with tertiary butyl hydroperoxide with the diethyl tartarate, formed a complex of this structure. You have here enantiotopic phases of alkene, but when you add to it chiral molecule, these two phases in this particular complex became or formed as a whole two different distereomers with different energy. Now we are expecting it will proceed with different energies, with different rates, and the enantiotopic excess will appear in the products. You get the point? We can say it again. He started with allyl alcohol, then formed with titanium alkoxide and the oxidizing agent tertiary butyl hydroperoxide and diethyl tartarate as a chiral ligand, formed two different diastereomers as intermediates in processing the reaction that will lead to different rate of formation of the enantiomeric products, okay, the epoxide, and we can get finally product with enantiomeric excess. Okay. Diol syn-Orientation. Converting an alkene to glycol dihydroxylation with syn stereochemistry require adding of hydroxyl group to each end of the double bond from the same direction. Reagents are available and the most common are osmium tetroxide and potassium permanganate. So, taking alkene, treating it with osmium tetroxide in sodium hydrogen sulfide or potassium permanganate dilute and in presence of base. Cool. That led to the formation of syn addition of 2OH. Osmium tetroxide dihydroxylation. The osmium tetroxide adds across the alkene in a concerted process via what we call it 3+2 cycloaddition, 1,3-dipolar addition. The cyclic osmate ester that result can be isolated and then treated with reducing agent like sodium sulfite or sodium bisulfite to reduce osmium 6-osmium metal, preventing reforming of ester and to produce a diol. Here is the reaction mechanism. It's either 3+2 cycloaddition or 2+2 cycloaddition. For the 3+2 we have here 1, 2, 3, so 3 here and 2 in here, so 3 plus 2 cycloaddition to form the cyclic osmate ester, which opens with water to form the diol in the same direction, or you start first by 2+2, 1, 2, and here 1, 2, to form 4-membered ring, followed by ring expansion to form again the cyclic osmate 5-membered ring like this one, okay, but through 2+2 cycloaddition, which again opens with water to form the diol. This method can be used to convert alkenes into diol in fairly high yield, but there are several disadvantages. In particular, osmium tetroxide is expensive and toxic. Expensive and toxic. To deal with this issue, several methods have been developed that use co-oxidant that serve as regenerate osmium tetroxide as it is consumed during the reaction. In this way, osmium tetroxide will function as a catalyst, not in a stoichiometric amount, just as a catalyst, catalytic amount, so even small quantities can produce large quantities of diol. Typical co-oxidants include N-methylmorpholine N-oxide, NMO, and tertiary butyl hydroperoxide or even hydrogen peroxide. So we start with osmium 8, form the cyclic osmate. Osmium is here is 6. Then water gets in and gives the diol, and the osmium coming out of this reaction oxidize again with N-methylmorpholine N-oxide to give N-methylmorpholine and osmium tetroxide, once again osmium 8. Tertiary amines such as dimethylaminopyridine, pyridine accelerate the addition. The first step is that the tertiary amine adds to the osmium tetroxide, creating oxygen has a negative charge, accelerating the addition on the double bond, 3+2 addition, to form an intermediate containing the ligand. Then the ligand gets out to form the cyclic osmate intermediate. Well, if that is the case, then the two enantiotopic faces of the double bond, okay, they are enantiotopic faces. When it gets into be a part of this complex, if the ligand is chiral ligand, these two faces will be a part of diastereomers with two different energies, two different rates, and we get two different amounts of the enantiomers as a product, final product. The use of chiral amine enable enantioselective conversion. So Sharpness realized that, and he used the chiral kinine ligands and add to his chemistry innovation. Permanganate dihydroxylation. Like osmium tetroxide, permanganate add to alkene double bond to form a cyclic ester, manganate ester in this case, not osmate, manganate ester. A basic solution hydrolyzes the manganate ester, liberating the glycol and producing brown precipitate of manganese dioxide. So we have cyclohexene with potassium permanganate. We get manganate cyclic ester, which opens with hydroxide to form cis-glycol in 49%. Osmium is much more bitter, gives high yield, but as we mentioned, it's toxic and expensive. Permanganate is cheap. And we have to be watching potassium permanganate condition. It has to be dilute permanganate in presence of base at low temperature. Predict the major products of the following reaction. Cyclohexene with permanganate in water, cold and dilute. We add the OH and OH from the same direction. Syn addition. Since we have here symmetry in the molecule, it is meso compound. It's meso compound. When we start with cyclohexene, using peroxyacetic acid in water, we get 1R, 2R, cyclohexane 1,2-diol, and 1s2s cyclohexane diol, a racemic mixture. Starting with cis bent 2-ene, osmium tetroxide in hydrogen peroxide, 2H in the same direction, syn addition, again we get 2s3s, 2r3r racemic mixture, again racemic mixture. Starting with cis bent 2-ene, but this time peroxyacetic acid in water, anti-addition of 2 OHs, we get a racemic mixture of 2s3s, 2r, 3r. Starting with trans bent 2-ene, but osmium tetroxide, hydrogen peroxide addition, OH syn. Okay, notice that when we start with cis and use the reagent which give anti, we get 2s3s, 2r, 3r. When we start with trans but osmium tetroxide and hydrogen peroxide adding OHs syn, notice we get the same 2r, 3r, 2r, 3r, and we get 2s, 3s, 2s, 3s. But this time, here we start with cis, and the reagent give anti-addition. Here we start with trans, but the reagent gives syn addition, and the products are the same. Trans bent 2-ene with peroxy acid in water to give anti-addition, we get 2r, 3s, 2s, 3r, again racemic mixture. Show how you would accomplish the following conversions. Cis-hex 3-ene to meso-hexane 3,4-diol. You start with cis, which has plane of symmetry. You have to reach meso, which has an plane of symmetry. You have to add the OH symmetry, so you use syn addition. To get syn addition, you use osmium tetroxide in presence of N-methylmorpholino N oxide or tertiary butyl hydroperoxide or hydrogen peroxide. Okay? So you start with symmetric, and you would like to get meso, which is symmetric. Then you have to add the OHs from the same side. Now you start with cis, but you would like to get D and L, racemic mixture. So you start with symmetric, then you add the OH anti-addition to be able to get racemic mixture, D and L. How to do that? You use epoxidation with peroxybenzoic acid, and you ring open using acidified water. Now, if you have the trans and you'd like to get meso, which has symmetry, so you start with the trans, you do anti-addition, you get the meso structure. So you form the epoxidation, the epoxide, using the peroxybenzoic acid, and then you open with water. So you get the OH up and in the back. Okay, if you rotate around this carbon bond, you get the methyl up and the OH out, and that's the mesostructure. Now, if you have the trans which has no plane of symmetry, okay, and you would like to get a racemic mixture, the only thing you have to do is just have the OH from the same side using osmium tetroxide. If we do it mathematically, if we say cis, syn, and meso, all of them are symmetrical, give it +1, and the trans and the anti and the racemic, you give them -1. We are talking about symmetrical alkene, symmetrical alkene and symmetric reagent. Okay, which means that you have to add, you are adding two identical groups, in this case two OHs. Then cis plus syn addition will give meso. +1 time +1 give +1. Okay, cis +1, anti -1, then you get minus racemic mixture. Trans alkene, trans means minus because there is no plane of symmetry. Okay, syn +1, -1 times +1 minus, then you get racemic. Trans -1, anti -1, then you get mesostructure. See you in the coming lecture. Bye bye.